In this lesson, we're going to pick up where we left off. Last time we talked about some of the Greek ideas and how, while they were pretty impressive in terms of their accuracy, they didn't really have a great basis for a lot of them. One guy that we talked about at the end was Aristarchus, who claimed that everything orbits the sun. And the problem was that he just didn't have the evidence for it. But some things that it led him to try to do was measure the ratio of the distance between the Earth and the Sun and the Earth and the Moon. And his method was pretty sound. He just was off by about 1,000 times because of a slight degree error. But in any case, what happened was there was a progression of sort of the accepted model. And that went through people like Plato and Pythagoras, and ultimately to a guy called Aristotle, who kind of synthesized it all together and put together a model that everybody pretty much liked, at least for quite a while, several hundred years. And it was the crystalline sphere model, or the celestial sphere model, and it used spheres which everybody liked, and lots of spheres. And he actually used either 47 or 55 spheres in a very complex model. It was kind of like the clockwork gears. One gear turns one way, another gear turns a little bit differently, and so you could scale up the speed or scale down the speed based on the way that the circles interacted with each other. And he used some geometrical tricks, but it was pretty much like gears moving the planets around. The thing is what it ultimately came down to is what caused one sphere to move a little bit differently than another sphere was the sort of intelligence animating each of the spheres. So they put different like Greek gods moving each of the different spheres, and that resulted in the different speeds. And they kind of assumed that these deities would move things in a pretty regular fashion. The actual celestial objects like Mars and Venus and so on were embedded in spheres made of different materials, which kind of also gave them different properties. And one of those materials was a property that actually crops up a lot in natural philosophy and later on in physics even, called the ether. And he also made a sphere at the very edge, which was called the sphere of the prime mover, and this was sort of an unchanging, it was an unchanging pattern of motion that gave rise to all other motion for all other celestial objects. And attached to that was a sphere of the fixed stars. And I'll show you a picture to kind of explain what I mean by this. So you had the sphere of the prime mover on the outside, and this was what gave rise to all the other motions. This motion moving at a certain rate ultimately gave rise to all the other ones. And you had the sphere of the fixed stars. And the idea was that you basically had the stars plastered all the same distance away from the Earth, all on sort of the edge of this crystalline shell. So they had all the stars pretty much the same distance away from the Earth. For the most part, this model makes a lot of sense. There's a little bit of weird stuff going on with Mercury and Venus and the Sun and Mars, the order there, primarily because Mercury should be closer to the Sun than Venus. But in any case, Venus does often appear close to the Sun. It's the morning star or the evening star for a reason. And so to put it near the Sun in terms of its motion along these pathways means that you're often going to get Venus near the Sun, at least as viewed from Earth. The whole idea behind these fixed stars, though, is really down to something called parallax, which we'll talk about later on. And basically, the stars all look like they're about the same size. They all move the same amount relative to each other, and that's something that I showed you in the first lecture that I did for this unit. So they're all moving the same relative to each other. They all look about the same size, about the same brightness. Some are a little brighter than others, but that doesn't necessarily mean that they're further away from each other. It just means that the stars are maybe a little bit different from each other. So that was the idea behind this sphere of the fixed stars. And we only had this number of planets. We didn't have some of the ones that are further away from us. They didn't exist at the time. So this was Aristotle's universe. And one of the sort of non-scientific principles was everybody kind of knew that this didn't work out that well. The measurements were okay. It gave a decent idea of what was going on. And so if you were navigating, you'd be fine because the stars were pretty easy to use. The planets were harder to use as navigational tools because they were more fickle. That's why they were called planets, which means wanderers in Greek. But the biggest problem was that sort of backward motion and forward motion that we saw with Mercury in comparison to the fixed stars. So we needed to come up with some better models. And some things that happened, well actually I didn't quite finish my thought there. One of the problems was, even though we knew this wasn't quite accurate, it was proposed by Aristotle. And this is a problem that science still faces nowadays, which is that if a big name person, if somebody who's done something successfully, even in a slightly different field, Aristotle, it was very different fields. He was very good at the arts and that type of thing in terms of philosophy, but not so good at science. But nonetheless, because he was Aristotle, his model was a predominant model for quite a number of years. Not just because of its accuracy, which was okay, but because it was Aristotle's. So one of the things that happened is over time, over hundreds of years, the stars and planets changed their positions compared to the Earth. So you had some motion. Basically, if we were looking at the position of one star one year and one star another year, we'd see slightly different results. And I'll show that to you. So here I have a star called Spica, and it's this one here, and it's a pretty large star in our night sky, so that's why I chose to use it. And if I change this is the year 2000 that I have it. If I change it 2001, 2002, 2003, 2004, you can see it just goes through pretty much this 4-year cycle, which isn't a big deal. These are just minor variations. We do the leap year adjustment and everything goes back to how it ought to be. But if I do it, well, here's 20 AD, and you can see that it's in a completely different part of the sky now. Well, not completely different part, but a very different part. And so that's 200. And I can go and I can make this 500. You can see that it changes pretty dramatically. And I can make this 1000. And now it's moved quite a lot. If I make that 1500, it's moved even more. If I make that 2000, it's moved even more. And I can go ahead and make that a 5000 if I really want to. And now we've lost it. I don't even know where it is. So it definitely changes. And even those small changes that we saw from year to year, without the advent of the leap year, it would have been very difficult to account for that. And so the models would get off each year and they'd have to make adjustments. And some things worked out well, some things didn't work out well. So there was a need really for a more accurate model within a couple hundred years after Aristotle. And that's just the stars. The planets' positions were even more tenuous to begin with. And so those changes became more and more pronounced as time went by. And certainly people tried to improve upon Aristotle's original and keep it up to date. But if you constantly have to update your model to make it accurate, it's not leading the predictions. You can make predictions that kind of work out, and then you change the model, and in each year you kind of have to readjust and readjust and readjust. In addition to that, there was new and somewhat improved data had been collected within a couple hundred years of Aristotle. And this was largely done by a guy named Hipparchus, who is kind of credited with being responsible for the development of trigonometry. Very brilliant mathematician, also very brilliant observer. So he cataloged hundreds of stars. He discovered something called the precession of the equinoxes, which maybe I'll explain in class. It has to do with the changing tilt of the Earth's axis. But in any case, people started realizing, this model we have, it's not keeping up with the data that we have. It's not that accurate. And at the same time, they didn't want to abandon any of the major principles of the Aristotelian model, which would be using circles, making it Earth-centered, that type of a thing. So we're going to pick up with how the model then became more accurate, the people responsible with that, and really the one person largely responsible for it for many, many hundreds of years. So that's what we'll pick up with on the next lecture.